record. Okay, so last class we stopped around this slide when we wanted to know which bearing is carrying the load. Okay, what loading I'm talking about is the thrust load. And what happens that we talked about the concept of being, the bearing being squeezed. So the best way to illustrate this is to go over this example. And in the first one, if you look, the casing, which is this one, as you see, these symbols indicate that the casing is fixed, which is, I think, the most common situation in the industry. And then what happens is that there is a thrust coming to the shaft. This thrust can come from within, like due to gearing or whatever. Sometimes it comes from the other machine, which is coupled to this machine. Now, there is a thrust, so something is pushing the shaft forward. The casing is fixed. And what happens is that, look, if you look carefully over here, you will see that this is the cup, right? This is the cup over here, and the cone is the one inside. And if you look, this is the cone. Now, the cup is restricted from movement by the casing. And I'm putting these two arrows to indicate that the case, if you push the cup this side, the casing will push from the other side. Okay? Now, at the same time, we know that the step over here, look at it. I'm going to show it to you very clearly right now. Do you see this step? This step is pushing on the cone. So what happens is that we have the cup and the cone being squeezed, one by the action of the shaft as it moves, the other one is by the casing as it reacts. So bearing A, or this bearing, is called bearing A. So it is a convention here in this book to determine which bearing is being squeezed and then call it A. What does squeezed mean? It means it will carry the thrust load. Okay, now there is another example which may look weird, but in here we're assuming that the shaft is fixed. The shaft is solid, fixed, and somehow there is a thrust pushing on the entire casing. Now, the same analogy, if the shaft is not moving, then this is a step which, if you push the bearing on, it will push you back. Okay? At the same time, as we know, there is here the cup over there. Sorry. So let me clean this up from here. You see, the cup over here is also, being pushed by the entire casing. Do you see that? So the shaft is pushing with these arrows and the casing is pushing with these arrows. So we ended up with two forces acting on the bearing, and it is being squeezed. And in this case, bearing A is the one which is taking the thrust load. Do you see that? So how we determine, like numerically? Well, what did we say? This is like visually by inspection, but in general, from a design and analytical point of view, what we can do is this. We say, okay, bearings are mounted on the shaft like this. Like, look, This is the cone, this is the cone, back to back or front to front. Now, this point over here, which, by the way, if you go back to the drawing, I don't know if I put it here, over there, this is it, A. You see that little A over here as a dimension? This is how much from this side, which is the outer like line of the bearing, you go inside a little bit. That little bit is how much deeper your effective point is going to be. And that effective point is here and there. Good. So the radial load on the bearing, so there is a radial load acting on the bearing like this, but when it goes to the roller, this load will come in here, and then it will get converted into a radial load and axial load. So we have this one, since it is opposite, it will go in the opposite direction. And of course, the radial load will stay down, okay? All right, so what will happen now is this. We have two induced forces. This induced force is FIB, and this one is FIA. How do we calculate them? Just to remind you, we calculate these two forces by this, which is, this equation says that Fi, so FIA, FIB, it doesn't matter. This is the induced force. The induced force tells you, tell me how much a radial load is being applied on the bearing. And then multiply that radial load by 0.47 and divide it by K. Now, 0.47 is easy. FR is easy. Do you know why? Because it's the reaction. If you have a bearing here, A, and there is bearing B, and there is FZ, okay, and there is Fy, all what you need to do is to find the resultant force. That's Fr, which you are going to use here. So it is just a summation of forces, summation of moment, and so on. Now, the 0.47 is constant. What is K? Well, in this particular slide, we told you you can start by approximating the K as 1.5. The question is why? Why? Why there is no table? Why there is no equation? Well, K is part of the bearing specification. So if you know it, you should know the bearing. And how funny it is, you are asking we are asking you, tell me what kind of bearings should you pick, and then we are asking you to know K. If you know K, this means you know the bearing. If you don't know the bearing, you don't know K. So we will use K as 1.5, and then we will teach you how to correct that. Now, what happens is this. What you need to know is the following. So that if you look here, this is FAE. That's the applied like axial load, or the external axial load, whatever it is. Okay? This has nothing to do with the bearings. And then we have this one going in the same direction, and we have this one going in the opposite direction. So you see where I'm going now, right? Two of these are going to be added up. Now, let's assume that you decided to call this one negative x, this direction, and this one as positive x, which means that FAE plus FIB are both negative. And what happens here is that we will compare these two with this one. Why? If the two red forces become as a sum bigger than FIA, it means all of the thrust will go in here. So bearing A, or bearing in the left, will take the thrust load. And be careful. I'm gonna say this very, very precisely. When we say bearing A is going to take the entire thrust load, do you know what are we gonna do? We're gonna say that this bearing will have an FE, an equivalent radial load, which is equal to, if you recall the equation, X, F, something, F, R plus, then there is a Y, F, axial, and something like that. So what is this equation? It is this. Look at it. Over here. What are we saying here? Be careful. You are, if you go home, you're probably not going to believe this, so you need to hear it from me. We're saying that the bearing, which will take the thrust, will be subjected to both thrust loading, which is FA, axial, and radial load, with X and Y being determined as K and 0.4. This is the equation we used when we have a thrust and axial. Good, that makes sense. Tapered roller bearing should be subjected to radial and axial load. Why I am making a big deal of it? Well, because the other bearing will only have radial load. That's funny, right? So even the thrust load generated by the bearing on the right will go to bearing A, and bearing B will feel only radial load. That's what we are assuming. You got that? Okay. Now, you will see how weird it is, but I want to make sure being weird doesn't mean it is difficult, huh? I just want to remind you, because you might think about it later and you feel confused. How? How is a tapered roller bearing, which should be subjected to both radial and thrust, has only radial? How? It's because the other one is taking the thrust. You get that? So that's exactly what are we going to do. So in summary, look, in summary, we are going to measure FIA. Okay? FIA. You ask me, what is FIA here in this sense? We call this bearing A, we call this one B. Now, we decided that FIA is alone because its thrust direction is going in the right-hand side, while these two go in another side. So if the case is reversed, you reverse the number. So there are two going in one direction, and there is one going alone. So what do? We compare this one alone with the other two. In the case, and don't be surprised, sometimes this alone by itself is bigger than both of them. Maybe, who knows? So if it is less than, which maybe you expect this, there are two forces combined, they will be more than one, which I said maybe not always the case, but if this is the case, then what will happen? The poor guy here will take all of the thrust. And if it takes all of the thrust, the equation will become as follows. If EA, the equivalent radial load at A, is coming from the radial load at A multiplied by 0.4 plus KA, which is a geometrical bearing factor, and then multiplied by the summation of the other two loads, which are the axial loads, right? This is the axial load. The axial load coming, two of them coming and being applied on FA. What happened? If FIA is greater, so this little one alone is bigger than both of them, then FB will take the thrust. And I want you to be careful. When FB take the thrust, we find the equivalent radial load at FB by multiplying 0.4 multiplied by FRB, and then KB, which is now the geometric factor for KB, which is for bearing B. And then what do we have here? FIA, which is this thrust minus this one. The difference will be applied on B. Good. Now there is one comment. I mean, look. In the first case, the other bearing will only feel radial load in the first one. In the second case, FAE only gonna have F radial. Okay, so the entire thrust, whether it is added or subtracted, it will go to the other bearing. It says here, in any case, I don't know, if the equivalent radial load, so FAE, the equivalent radial load, is less than the original radial load, then you should use the original one. Okay, in any case, if the radial equivalent load is less than the actual radial load, then use the actual one. Don't use the smaller one. Now, how do we proceed? We know the forces now. That's what we wanted to do.
Okay. Use where?
Yeah.
It says use the equivalent radial load, but is it used somewhere else or in these equations themselves?
If in any case of these, the equivalent radial load, in any case of these, like this one, for example, FEA, let's assume, just for the sake of assumption here, if FAE is 100 and if FRA was, for example, 200, then you should use the equivalent as 200, not 100.
Okay, got it.
Okay. Now, how do we pick bearing? Well, if you recall from the long discussion with roller bearing, the ball bearing, we came up with two equations in reality. The first one is a catalog number C10 for 10 percentile, and which is 90% reliability. Okay, and let's say you are satisfied, you want 10th percentile with 90% reliability, and that's it. That's what you want. If that's what you want, then maybe you have a different force, different rated force than the different desired force than the rated force, or different speed, or different life. In that case, you use this equation where D stand for the desired entity variable, and R stand for the rated one. I should remind you that in the book, the table provided for tapered roller bearing in figure 1115 are for Timken. And Timken says, if you remember long ago, we said that the L rated for Timken is what? Anybody remembers? $90 million cycle or revolution. Other kind of bearings, they have L rating, which is 1 million. So be careful. We are here using tapered for Timken. So LR is going to be 90 multiplied by 10 to the power 6 revolution. طيب, what happens if we need different reliability? If you remember, we use these equations. Either one. Mostly we use this one. This is just an approximation here for the natural logarithm. And I don't think in the class or in the quiz, you don't have a calculator, you will be able to find the ln 1 over RD, so it's not difficult. Now, these equations are built for what, ya shabab? For a desired reliability. Now, one thing which we need to ask, what about x0, theta, and b? Are they the same? Because we know that the Weibull distribution parameters for ball bearings, where we use them several times, now we have a tapered bearing. And if you guess it, yes, then yes, they are different. And interestingly, as you see over here, x0 is equals to 0. That's very nice. It will shrink down the size of the equation. Theta is equal to 4.48 and b equals to 3/2. Don't forget that a in here is what, ya shabab, for cylindrical bearing? How much is it?
10/3, I think.
Yeah, it is 10/3. Good. So let's have an example over here, okay? This is very important. This is gonna sum up everything in your mind. Now, for this example, I am not going to go over the calculation of the reactions. Just what you need to know here is that we, as usual, have A over here, a bearing, and there bearing B. Okay, so there is a bearing A and B. And we have a helical gear. Now we are gonna have one full chapter for one full chapter for helical gear and worm gear and so on. But what you should know is that when you have a helical gear and you apply a force on it with an angle, whatever, what you are gonna get is a radial force, a tangential force, and an axial force. 3. So that's the source of axial loading over here. Now, what does this mean? It means that this bearing will have F A along the Y. Sorry, this is supposed to be Y. And F A along the Z and FA along the X. Right? The question is, which of these two bearing will take the thrust load? Now, what do we need to do? As usual, we need to go and sum up the resultant over there. And once we know the resultant, that's it. Do you remember what we should do? We multiply by 0.47, multiply by the resultant, divided by K. And then we find the induced thrust at A. We do the same at B. And then we analyze, is the sum of the thrust is the same, is it different, and so on. That's the process. Yes?
K will be 1.5?
We will start with 1.5, yeah. Don't worry, this is what are we gonna solve. Now, so what is given to us over here is that if you look, let me use a better color. The F radial is equal to 1,770 Newton. F thrust is equal to 1,690 Newton. This is on the helical gear. And then we have F tangential. So this is, let's call it axial. This is the thrust. Tangential 3,980. And then what do we have also? We have the pitch diameter over this, which is the diameter that we use to calculate the torque. So then we have a speed ND, which is equal to 800 revolution per minute. And what do we have? We have LD in hours, which is equal to 5,000 hours. And we want the reliability of the bearing set. If we say the reliability of the bearing set, this means the desired reliability is the square root of the set of the reliability for both bearings, which is 0.99, the square root. That's the goal. That's the reliability, the desired one. Okay. And we want to use single row tapered roller Timken bearings. Timken bearings, it means that what? L rating is 90 multiplied by 10 to the power 6. Good. Now, what are we going to do? If you look here, as I mentioned, we are going to find RZA, RZB, right? And then RYA and RYB. And by doing so, what will happen? We will be able to find the radial. Look, these are the radial forces. Now, this is the radial force, inclined this way, that way, it doesn't matter. This is the resultant radial load acting on the location of bearing A and bearing B. How is this going to help me right now? Well, if you look down, we are going to find the induced thrust, right? So for the first one, we have 0.4 multiplied by FRA, which is this one, and then divided by 1.5. What is 1.5? The first approximation for the geometry factor K. What do we get? 680. 680. Now, the other one, we do the same. We get 832. Remember, FR is this. Okay. Now, if you look at this, FIB, right, which is going to go this way, and look at the thrust. It's going also in this direction. So I will calculate FIB, which is equal to 832 plus FAE, which is equal to 1690. I mean, ya shabab, without calculator, if you look at these and compare them with this, which one is bigger? The sum. The sum of this one plus this one is bigger than this one. What does this mean? Anyone?
The thrust is on A because FIA is less.
Yeah, the thrust FIA is tiny, while the FIB plus FAE is bigger. So all of the thrust will go to A. Now, what does that mean? Let me clean this so you don't get confused. Okay. Now, what is this? Well, if you remember, we said that FEA will be equal to 0.4 multiplied by FRA plus KA multiplied by FIB plus FAE. Now, this is a constant. FRA, we calculated it. It is this one, 2,170. So this is 2,170. This one, 1.5. This one is 832. And this one is 1,690, which is this value. And this one is this value. What do we get? We get 4,651. Now, what about this? If equivalent B will be only 2,645, as if B is only subjected to a radial load only. Now, if we do this, ya shabab, then what will happen? We can go to the next step. The next step is to calculate XD. Now remember, we have a desired reliability of a square root of 0.99. So the desired reliability is 0.995, which is more than 90. So you need to use the equation with the desired reliability, which is this equation. Now, this equation, ya shabab, what does it have? On the top, it has XD. Now, XD is equal to LD divided by LR. LR for Timken is 90 million. So this is the 90 million. Now, what is this? This is LD in hours, 5,000 hours. This is in D, in revolution per minute. And this is the conversion factor. So what did I get? I got 2.67. The desired reliability is the square root of 0.99, which is 0.995. If you do this for bearing A, remember bearing A, if you go back, was subjected to a resultant radial load of 4,651. So there it is. Over here, I forgot to tell you in the question, it says that the application factor AF is equal to 1. So we got rid of it. Now, what is this, ya shabab? What is 4.48? What is it?
The theta.
Theta.
It's the theta. And then we have minus 1 minus the reliability. Okay, so here in the solution, he is using this equation, ya shabab. There you go, this one. Did you see that? Which is fine. We said that both of them are the same. So, and then I need to clean the board over here. I want you, what is this? 2/3, which is the Weibull distribution of what? Look, the Weibull distribution over here is 3/2. But because we have 1/b, it became 2/3. Similarly, in here, we have what? 3/10, not 10/3. Why? Because it is 1 divided by 10 divided by 3. That's why. So be careful. That's a very simple mistake you can make. Okay? And this is the dimensionless life factor. And what do we get? We get 11,486 Newton. That's a C10. Okay? So what does it say in the solution? It says that if you go and look, you will find TS 15100 and a cone, which is, and a cup of 15245. What does that mean? Which will work with Ka. Now look, this is the actual K, which is 1.67, and this is the C10, the catalog value, 12,100 Newton. So let me show you the catalog. So this is the catalog, if you look at it in your book. And what are you going to see? You are going to see, honestly, maybe did I make a mistake over here? Can you give me 1 second, Yeshua? No, I think this is it. So if you look, this is the cone, this is the cup. And these numbers will identify what is the cup, what is the cone. So this is like the ID of the bearing. That's why you see them in the solution. Next is K. So there you go. That's why we have to approximate it. Now we know the real value. And look also, we can get the radial load in Newton and in pound, and what? The thrust load. Now we don't look at the thrust because we use the equivalent radial force in order to judge which bearing using this only, not both. You got that? Now the question is this: we made the entire calculation based on 1.5, and now we are picking 1.67. So what should we do? Should we just say it's okay?
We should calculate again and we see if the assumption is right. Or the approximation is good.
Did you say, Ali, we calculate them again?
Yes.
Yes, so that's exactly what are we going to do. So in here, if you see quickly, this is the calculation for bearing B. Of course, bearing B will require less load than bearing A because it does not carry a thrust. And using the same bearing will make it more reliable. That's fine. Now, what we need to do is to go and start from the FIA, because K will change it. Now in here, we were asked to use the same bearing. If you were not asked to do that, then you will have a different values for KA and KB. But since they are the same, this will ease up the calculation, 1.67, 1.67. Now recall that the radial forces will not change. Those comes from the external loads. They will not change. What you have here is 0.47 multiplied by the radial loads divided by 1.67, and here you get the new induced loading. Okay? Now, apparently, ya shabab, if you look, you will see that FIB plus FAE, which is 747 plus 1690, this will not change. It is still the same. Is definitely as a sum bigger than 611. So the same assumption hold that thrust, the thrust will only apply to bearing A. Now, if you remember the equation, what are the factors now that will change? 0.4 is the same. FRA is the same. The FAE is the same. What changed is FIB and KA. By changing these two values, what did we get? We get 4,938. How much was it before? Let me see. It was 4,651. Now it is 4,900. So it's a little bit more. Okay. FEB will still be the same. Why? Because it is equal to the radial load, and the radial load didn't change. So if we recalculate, we will get this as what, ya shabab? As 12,195 Newton. This is more than what we picked. We picked 12,100 Newton by 95 Newtons. So in the solution here, it says it's okay. It's manageable. So we are still gonna use the same bearing. And of course, for the other bearing, you will get a different load. No, it should be the same. It should be the same. Nothing changed. This is 6,554. And if you look here, this is 6,554. I mean, nothing changed. So what happened is that what is written here as a note is that what you need to understand is the fact that this 150, okay, this 150 from here to there, that's 150. If you go to the diagram of the bearing, you will see that if the bearing is sitting here, okay, then what will happen is, no, it's actually not like this. maybe I should draw it in a better way. So if the bearing is mounted in here like this, and the other one is like this, then you should understand that there is a little bit here and a little bit here. This dimension is A and this dimension is A. So in here it says that this 150, you will eat from it twice to 5.8. A is where? Is here. Let me show it to you. That's the A. Do you see that? In millimeter and in inches. So it is negative. Why it is negative? Because it is inside the bearing. It goes inside the bearing. And this is just to teach you that the effective length is not exactly 150. It is that 150 minus 5.8 from the left bearing minus 5.8 from the right bearing. And it is exactly 138.4 millimeter. Understood, ya shabab?
Yes.
Yes, Doctor.
Yes.
How do we judge if the load that we got by 95 mol is manageable or not?
Yeah, okay. Here it says, let me show you. Look what it says. It says, although this catalog entry exceeds slightly the tentative selection for bearing A, we will keep it since the reliability of bearing B exceeds 0.995. In the next section, we will quantify how the combined reliability of bearing A and B will exceed the reliability goal of 0.99. What does this mean? What does this mean? It means that إحنا, what did we say? We said that the reliability set, both of them, okay, is 0.99. So we took the square root of it and we got a reliability of 0.995. Now, if you, and that's what we are going to do next class, if you take the catalog value, the catalog value is 12,100 Newton. Sorry, not 12,100 Newton. Okay, this is the catalog value. If you take it, take the Weibull distribution, put A, put B, everything here. Solve for R. Solve for R. For bearing B, the reliability will be higher. Why? Because you are using high rated bearing for a low load situation. The load here is only 6,000, right? That's what we are saying here. While the load in here is 12,000. And we are still using the same bearing. Do you get that? So what happens? It says that the overall reliability, because of bearing B, will increase and it will be okay. We will see this in the next class. Okay? So for next class, you will know everything in reality. Okay, I need to stop over here, ya shabab, now, and share my screen to take your attendance. You can leave right after if you want. Okay. Yusuf Yusuf?
Yes.
ماجد العباد.
Yes.
حسن.
Yes. العياش.
عبد الرحمن.
Yes, عبد الرحمن بايجان.
محمد دعبوس.
Yes, دكتور.
عبد العزيز.
Yes, دكتور.
أحمد دوسري.
Yes, دكتور.
عبد الإله.
Yes, دكتور.
خالد.
موجود دكتور.
مش مصلح.
Yes, دكتور.
سعود.
موجود.
عبد الله حجاب
Yes. Yes.
سلمان
موجود.
فارس جبرين
يس.
طارق
موجود.
عمر يا مصطفى
يس دكتور.
ويسر علي
Yes, yes.
خالد العتيبي
يس دكتور.
حسام
يس دكتور.
هاشم
Yes.
سلطان
يس دكتور.
سلطان الحربي.
اي نعم دكتور.
اوكي نو الصبحي. اوكي نايف
Yes.
محمد
يس.
عبد الله الزهراني
Yes.
مشعل
يس.
جعفر
Yes.
مؤيد
يس.
علي
Present.
علي is here
Yes, yes, Dr. Amir.
and حسن. That's all.
لو سمحت دكتور،
Yes.
انا من السكشن الاول ارسلت لك ايميل زياده بيتي.
Okay. Okay, just wait a second, okay?
اوكي.
Zion. Yeah, okay, Zion.
يعطيك العافيه.
Problem. Yeah.
Doctor, there's a question I have regarding the homework.
Uh-huh.
In problem 3, there's a tangential force in the ball bearings, and I'm not sure if we've dealt with it in class.
A tangential force?
There's a thrust force, there's a radial force, and then there's a tangential force coming out of the page.
Let me see. Problem number.
It's problem 3, but it's called problem 2. There are two problems too, but the third one is, yeah, talking about the third question.
Wait a second.